Okay, we're in business. So last time we were talking about vector fields, and in particular, the book has this section 3.4, where they introduce certain topics way in advance. The idea being, I presume, to kind of plant certain thoughts in your head so that you can be kind of maybe anticipating as we go further on in the course, cogitating, digesting, whatever. So we're almost done with 3.4. There's a few more things that I'm going to introduce. The book presents these as a bunch of facts, such as these two right here, talking about what happens if you take the curl of a gradient, or what happens if you take a divergence and how that might relate to curl, etc. And there's several of these facts that can be noted. I want to show y'all a way to kind of combine all of those several facts that they mention into ultimately kind of one statement that just applies in different places in different ways, but it's basically still all one big idea. So step one is to recognize that we're going to compose these operators, gradient, curl, and divergence, in this specific order. Now, I emphasize this is something we can do because when you take the gradient of a function, you get a vector field. And curl takes in a vector field and then produces another vector field, which is what divergence takes in to produce then a function. So now why, other than the fact that we could, the Legos fit together this way, that's true. But other than that, why would we want to actually compose these is actually a pretty deep point. And it's well beyond what we can do in Math 219. And so I'm just going to say good things happen if you think of these operators as kind of fitting together in this order. And that's really all I can tell you. Other than, of course, when we get later on to chapter 6 and 7, we're going to see a lot of the really good things that are going to happen. But we're really going to have to wait till chapter 6 and 7 for those. The next thing I want to introduce is the idea of an exact sequence. I'm going to describe what an exact sequence is in kind of casual sort of terms. I'm going to do so with a particular metaphor that I find particularly satisfying myself. It's just a metaphor. Don't take it too seriously. But like I say, I find it very satisfying. So we're going to define what I call a lifetime. I'm going to take the fact that you can take a function, the fact that you can take its gradient, that gives you a vector field, the fact that you can then compute the curl of that, etc. And I'm going to kind of take all aspects of that and translate them into lifetime-related concepts. So work with me on this. It's just a metaphor, but I think you'll find it satisfying. Okay, suppose you have a vector field. Suppose you take the curl of that vector field. The result is a new vector field. I'm going to call this the passage of 1 unit of time. So I want you to think of going to the right on this diagram as being time. And again, it's just a metaphor. Okay. All right, next, if you have a vector field and if you take the curl, it is possible, I suppose, that you might get 0. And there's something, let's see how to say this. There's something about 0 that's kind of like death in a way. In the sense that, well, it's nothingness, if you will, right? Again, it's just a metaphor, but also you can't get out of it. In other words, no matter what happens after that, if you have a 0 here, take the divergence, fine, but you still have 0, right? So it's a kind of a nothingness from which you can't return. To me, that says death. Anyway, it's just a metaphor, doesn't matter. Okay. Here's another thing. If you have a vector field, and I keep going to this spot for no particular reason, it is possible that vector field might be the gradient of some function. It might be. It is also possible that there is no function whose gradient is that vector field. Each of these is a possibility. So what I want to talk about is this possibility here. What if you have a vector field for which there is no anti-gradient? If this is, this vector field did not sort of survive from this previous moment and it came from this previous time. This is in some sense the first time we're seeing this thing, right? It didn't exist in the previous time in any form at all. And so I'm going to say if this is the case, then this is where that vector field is born, if you will. Right? So we have these concepts now of time, of birth, of death, and with these ideas together, here's what an exact sequence is. An exact sequence is a sequence where all lifetimes are 2. And I claim this one statement encompasses a bunch of different facts, 2 of which I have noted right here. A bunch of different true facts about functions in vector fields and these operators right here. So, for example, you have a function. You take its gradient. To get a vector field, what happens when we take its curl? Now, wait a minute. The lifetime has to be 2. It was born there. It kind of has to die here. So this is what a lifetime of 2 would look like in this case. And notice I could translate that instead as saying that the curl of the gradient is 0, which is this fact here. Again, stated in the book, but I'm writing it like so. Okay, here's another example of how you can use this idea of a lifetime of 2. Suppose you have a vector field. Suppose that the divergence of that vector field is 0. Let's just say, hypothetically, well, wait a minute. If I have a vector field here, if its divergence is 0, 0 is death. So that means it died here, and everything has a lifetime of 2, not at least 2. 2. Exactly 2. So if it died here, it must have been born here. That means there must be a vector field whose curl gives you that original vector field. Notice that's this statement right here. If the divergence is 0, then that vector field must be the curl of some other vector field. Okay, so it's just a nice way to remember a bunch of facts, and there's several more that you could imagine. Just imagine the various different lifetimes of 2 and the sort of 2 sides of each one of those cases that you can write down. Anyway, I think it's a convenient metaphor. I like it. By the way, there's a version of this in 2 dimensions. That this is all 3-dimensional, I should have said. But there is a 2-dimensional version of this as well. We're not going to talk about that now. We'll talk about that in chapter 6. Yeah, is that a question?
But if there's a constant...
Yes.
Oh, sorry.
Yeah, no, yeah, that's quite right. I was just about to get to that. There's 2 things that I ignored deliberately in this, because I want to make the story a simple story, right? So you're quite right. Constant functions are non-zero. The gradient is 0. And it's a sad little story where it has a lifetime of only 1, right? But this is one of the very few exceptions to the rule. The other exceptions have to do with what I'm going to call regularity issues. And so if you have a function or a vector field where maybe there's a discontinuity or something's not differentiable, then all sorts of weird things can happen. That's not our problem, and I'm not going to worry about it. But good eye and good thought. There is that one exception. Yeah. Okay. All right. I just wanted to throw that out there. Therefore, I'm going to call that pretty good evidence. And by the way, you can check all these individual facts here for yourselves. And some of these might be homework exercises, as I recall. But various different facts you can check for yourselves, all of which together kind of suggest, hey, but this is starting to seem like a pretty natural thing after all. Right? You put these together and you get this broadly applied fact about lifetimes being 2. So maybe this is a natural thing to do, not just an arbitrary thing to do. We're going to see a lot more about that in chapters 6 and 7. Until then, let me just wave my hands a little bit and say, get ready to see a lot of relationships and connections and analogies, etc., between these operators. Okay. So that does it for chapter 3 for the moment. We're going to move on, you would think, to chapter 4, but no, we're going to go on to chapter 5. You might have already noticed this on the lecture schedule. Let me say a quick word about why we're skipping chapter 4. This is just for the moment. We're going to come back to chapter 4. We're going to do chapter 4 after chapters 6 and 7. The reason for this, ultimately, is because chapters 6 and 7 are challenging. There's a lot of ideas in chapters 6 and 7. I want y'all to have as much time as possible to digest chapters 6 and 7. I would like to get to chapter 6 and 7 as early as I possibly can. I would like to delay as much of the course as I can to after chapters 6 and 7, again, so you can have as much time as possible to digest chapters 6 and 7. And sadly, chapter 4 is about all we can. Everything else is pretty prerequisite to chapters 6 and 7. We need all the vector stuff from chapter 1 in order to be able to do chapters 6 and 7. Likewise, chapter 2, 3, and 5. So, but 4 is about optimization. It's important stuff. You need to know it, but not for chapters 6 and 7. So we delay that and then proceed with chapter 5. All right, does that all make sense? Okay. All right, so integrals. Y'all will recall that I kind of trash-talked partial derivatives a little bit when we were first starting chapter 3. And not that I'm opposed to partial derivatives. It's good stuff, very important. Got to have it. Right? All the other derivatives we talk about, we write in terms of partial derivatives. So yes, they're very important. But what I don't want you to do, you've heard me say this before, don't think of partial derivatives as being fundamentally what a derivative is. Right? Because that's really a pretty shallow point of view on derivatives. Derivatives are relationships between input changes and output changes, and the broadest, most general way we can say that is to talk about the derivative matrix that you multiply by input change vectors to get output change vectors. And so the derivative matrix is really the best way to think about derivatives. I start with partial derivatives partly because the book does, but partly also because it's easy. It's relatable. It's an easy first step that doesn't require a lot of effort. Okay, so we're going to do something similar now here with integrals. The very first example of an integral in multivariable that I'm going to show you is useful, necessary, and really not the way you should be thinking about integrals. So we have to do this way, but again, don't hang your hat on this point of view that we're going to do here. And I'll explain why. Okay, so first a quick flashback. Hope you all remember how to compute the volume of a rotated solid if you have an area like this. Right? And if you rotate that around the x-axis, that generates a volume. And how would you compute that volume? Well, you slice it up into a bunch of little pieces. The pieces of volume that you slice it up into, here, let me leave that shaded. The little pieces of volume that you slice it up into would be kind of like that, which are little sort of coin-shaped things like so that you can compute the volumes of, right? And the big trick for how you're going to compute this volume is that it's area times thickness. And good news, the area is easy. The area is just the area of a disk, and that cross-sectional area of a disk is easy to write down as just pi times radius squared. And I know you all have seen this all before, so let me largely leave it at that. Does that look familiar to everybody? Yeah. Okay. So the thing that makes it possible, then, to take this approach to computing this volume is that we know how to compute the area of a disk. Right? That's a garden variety, barnyard variety, easy old geometry formula that we can just use as needed here. Okay. All right. There's other versions of this where instead of having a rotated surface, maybe you have something where the cross sections are known for whatever reason to be like squares or equilateral triangles or something like that, where you can just kind of write down what that cross-sectional area is. Okay, so what would we do then if we wanted to compute this volume here? This being the volume sitting underneath a surface, that surface specifically being a graph. And how would we compute that volume? So you could start off with kind of the same approach. We can say, look, the total volume is the sum of the volumes of these slices, and here's a slice. Right? I can add up those volumes of those slices. What are those slices? Well, here's where I kind of get a little discouraged, because I suppose I could say that it's cross-sectional area times thickness, but what's the cross-sectional area here? This is not a disk. It's not a washer. It's not a square. It's not an equilateral triangle. It's not any sort of garden variety geometric figure where I can just snap right down what the area is. And in a single variable calculus class, we would bail, throw up our hands in frustration, and declare that we lose. Right? Okay. So here's the thing. We can totally compute this area. This area, here it is. This area here is the area under a particular curve. Where have we heard that expression before? Area under a curve. Integral, of course. Right? So, to be careful, of course, when we say we want to compute an area under a curve, integrals compute that for us only if we're looking at a curve which is a graph. Is this curve a graph? Well, it's a cross-section of a graph. The graph of the original function is this whole surface. Right? So, what about the curve? Well, the curve, you think about it, is what you get when you fix that value of y. In other words, when you take a cross-section perpendicular to the y-axis, and if you're fixing a value of y, and so I'm going to gray that out there, y is now fixed. Notice now, this curve gives me height, z, right? That's height as a function of, well, in fact, one variable. And height as a function of one input variable is a graph. Right? So, in fact, yeah, no problem. I can compute that area, no problem at all. That area is this integral right here. Don't forget, we are taking an integral of f of x comma y with the understanding that we're looking in this cross-section where y is fixed, y is constant. So that y not allowed to change as we're computing this area, for that fixed value of y. Right? So while at a glance it looks like you've got an integral where there's two variables on the inside, that's an illusion. You don't. There's really only the one variable. Y is a constant. So this is again, cosmetically it looks a little weird, but this is in fact a plain old, regular old, single variable calculus integral to compute an area. Let me pause on that for a second. What do you think about that? Is everybody okay? Okay. All right. So, it's kind of all over but the shouting at this point. We know the cross-sectional area, and so let's see here. Our cross-sectional area then, multiply your cross-sectional area times the thickness. Let's see here. Let me represent where is my thickness here. My thickness would be kind of like this, which is dy, because we're going in the y direction. So area times thickness gives you little pieces of volume. These are the pieces of volume then that we're adding up, and altogether, the total volume that we're interested in, that total volume is just that integral. Yes?
Does y have a value in the inner integral?
Yes, that's right. So for the purposes of that inner integral, let me clean up what I'm doing here. So for this inner integral, y is fixed at whatever value you're looking at. So at whatever value of y you want to know the cross-sectional area, that's the value of y. You fix that value of y. You compute this integral where you use that value of y fixed to be the thing here, and then you compute this integral of what remains as just a function of x.
But if you're doing like the iterated one.
Oh, yeah. No, yeah, we're getting there.
Y as like y. And
That's right. You'll see an example in just a minute, and I think that'll answer your question. Yeah. Everybody? Yes, question?
So if you're going to do the same thing for x, would you just switch everything around?
Yeah, that's a great question. We are going to do something pretty much like that. In fact, I'm going to leave that as kind of an exercise for you all to kind of work out by analogy, but it's exactly what you said. If you want to, and I don't want to go there just at the moment, but if you want to take your original volume and instead of slicing perpendicular to the y-axis, if you want to instead slice perpendicular to the x-axis, you're going to get a very analogous analysis here, and everything's just a little bit different, but it's all highly analogous. Yeah. And the details of that I'm going to let y'all work out, but we're not done working this one out yet. So let's work this one out first, get comfortable with this, and then I think you can do it the other way. Yeah. Anybody else? Okay. All right. So a couple of quick observations to make about about these integrals. First, a little terminology. It's called an iterated integral. This terminology has always bugged me a little bit. I mean, I get where it comes from because it's an integral of an integral, right? So, iterated. You keep saying the word integral. So, thus iterated. My problem with it is that we're not doing the same integral twice. There's an x integral and then there's a y integral. Those are different. Right, so I feel like it's not really doing the same thing twice in a row. I would like to popularize the term nested integrals because it's literally an integral inside of another integral. So, I think that makes more sense. But that's just not it's not really in the terminology. But I will see what we can do. I'm trying to promote that term. Maybe it'll catch on. Okay, iterated integral. You also have to keep in mind, while you're looking at an iterated integral, we've already talked about this a little bit, but while you're looking at the inside integral, don't forget the purpose of that inside integral is to compute this area. That's the area for a particular cross-section at a particular fixed value of y. So y is to be treated as fixed. We've already talked about that. I want to give you the slightly different point of view on it here, though. What that means is the outside variable, the variable for the outside integral, that's the one that you have to treat as constant. So this is a nice memory tool. You don't have to think about the geometric picture every time. You can just remember the simple rule that when you're dealing with an inside integral, the outside variable is to be treated as a constant. Is everybody happy with that? And that works whether you do it the other way or whether you do it this way. Okay. All right, now a little bit of lingo. It's tempting to call, let's see here, let me do it like this. It's tempting to call this the first integral because it was the first integral we wrote down. We had this big thing. We decided to slice in the y direction, and we were going to write down a dy integral, but we didn't know what the cross-sectional area was. So we then subsequently interpreted the cross-sectional area as this second integral. So you can see the temptation to call the outside the first integral and the inside the second integral. Here's the problem. When you start to compute this, you can't compute the dy integral first because we don't know its integrand yet. Its integrand is the dx integral that we haven't computed yet. So you have to compute the inside integral first, and only then can you compute that dy integral second. So which integral is first depends on what are you talking about, the formation of the iterated integral or the evaluation? One's first, the other's first in the other context, and so it's not clear which one is first. So I think the terminology should just be absolutely abandoned. I wouldn't call either of these first or second. What's very easy to do, though, is to just recognize that, look, one of them, colors. One of them is very clearly on the inside, and one of them is very clearly on the outside. The outside one is formed first and evaluated second. The inside one is formed second and evaluated first. But inside and outside are unambiguous. Everybody with me? Okay. All right. Let's crank one out. So we're going to compute the volume under the graph. Very important that this be a graph of this function. That gives us some surface like that. Whatever. We want to compute the volume underneath it. Specifically, the volume sitting over this rectangle. By the way, this is just notation representing a rectangle. The first interval here is telling us the x range. The second interval here is telling us the y range. And the rectangle then is, well, it's the rectangle that has those x values and those y values, and so this is that rectangle. Everybody get that notation? Okay, so we got a graph of a function, we got a rectangle, and we want to find the volume under the graph over the rectangle, which is exactly the question that we addressed here, that we have an answer for here. It's an iterated integral, so we're just going to write that down, and here is that iterated integral, and now it's just a matter of computing. So we're just citing the result we already got there. Okay. Now, there's a couple of landmines you got to watch out for. Broad stroke, this is just a matter of kind of plug and chug. Really, honestly, it's plug and chug. But here's where the landmines are. First landmine. When you're taking this antiderivative, whoops, let me do this in green. When you're taking the x antiderivative. Antiderivative of x squared is 1/3 x cubed. No problem. I know you all know all of your integration rules. Here's the landmine. A lot of students will forget that y is a constant, and therefore y squared is a constant. And if you aren't paying attention, if you're not actively thinking about the fact that, look, y is the outside variable, and therefore for the inside integral it's a constant. If you're not thinking about that, a lot of students will write down 1/3 y cubed. It's not. That's wrong. Because as far as this dx integral is concerned, y is a constant. So y squared is a constant, and the integral of a constant is that constant times your variable x. So x y squared is the antiderivative here. Is everybody with me? Everybody see what happened? You see how this is, right? You might get in trouble. You might accidentally oops on that. So heads up. Make sure you don't oops that. All right, the second little landmine. When you plug in these values, right, these are the values of x that you plug in, and a lot of students will just write down the 0 and the 1, and then just start plugging in those values, because that's how the fundamental theorem works. And you take, for example, 1, and you plug it in there, and you plug it in there. And if you haven't written down the little reminder that I put there, it's easy to just look and see, I see a 1, that's what I'm supposed to be plugging in for, and you might inadvertently, momentarily forget and also plug that in for y, and that's wrong. That 1 is not a value of y. That 1 is a value of x. Right? So my little hack for avoiding this problem is just be explicit. When you copy down this 1 right here, remember it is explicitly x that's equal to 1. So write it as such. Write x equals 1. It'll take you an extra 3/4 of a second to write down x equals, right? And it will save you the inadvertent, look, it happens to the best of us. There's no shame in it, but it might make a mistake, right? And so that's 3/4 of a second well invested in my book. Write x equals for these values that you're plugging in. That'll help you not accidentally oops it. Everybody with me? It's not required. It's highly optional, but I think it's good advice. Okay, everything else is just kind of details. You plug in, you evaluate. Notice, by the way, that we've gotten this inside integral computed now. That inside integral is this function. And it's which right off the bat is a little weird. Wait a minute, it's a function. I thought I just evaluated an integral. When you evaluate an integral, shouldn't that be a number? How come it's still a function? Well, don't forget, this y is a constant. It's a constant for the purposes of that inside integral. So it's going to kind of remain, if you will. Right? And so, well, it stays there because I didn't do anything to it. So, yes, it's a value, but it's a value that depends on y, otherwise known as a function. And here's a further reminder. Don't forget what that inside integral is. The inside integral is area, and area specifically cross-sectional area for a given value of y. So, of course it's a function, because that cross-sectional area clearly is going to depend on that y. Where is it that you take this y slice? Different y slices will have different areas, so of course this should be a function of y. What do you think about that? Everybody happy? Okay. All right, and now it's really 100% single variable calculus, evaluating this integral. And so make sure you're good with all your single variable calculus and algebra and arithmetic and such. And then you can crank those out reliably. Okay, so that's how an iterated integral works. Now, a couple people have asked already, what if you do it in the other direction? What if you do your slicing first in the x direction? Everything works through just fine. Everything's going to be a little different. Instead of having cross-sections that look like this, well, instead you're going to have cross-sections that look like that. And instead of y going from C to D, you're going to have x going from A to B as your outside integral. And that cross-sectional area, that cross-sectional area is going to be computed as y goes from C to D. So you can see it's going to track. It's going to, structurally anyway, it's going to totally track exactly what we did here. It's just that everything's going to be that little bit different. And I think this is a fantastic exercise. If you want to test to what extent do you really understand what happened here, try to reproduce the analogous argument, the analogous figure, where you slice it in the other direction. I think it's a nice little practice problem. Not required, of course, but I think it's a good practice problem. And the punchline is that, everything works out just fine. And so while we've previously shown that volume can be computed as a y integral of an x integral, y'all will show for yourselves that same volume can be computed as an x integral of a y integral. And you get the same answer either way. Is that satisfying? You believe it? Yeah.
Is that saying it only works, like, those two being equal only works when the domain is a rectangle?
Yeah, that's
Or
yeah.
only do the nested?
Yeah, no, that's a great question, and this is the next thing I was going to talk about. Notice that this question specifically says we're computing the volume over a rectangle, and this is specifically a rectangle. We are very soon, as in Friday, going to consider the question, what if you wanted to compute the volume over something that's not a rectangle? It's still, if I had a disk over here instead of a rectangle, that's still a volume. How would I compute that volume? And it will turn out that it's again going to be an iterated integral. It's going to be different, though, in a way that I don't want to talk about just yet. And those iterated integrals, you can't just take the outside bounds and make them your inside bounds like you did here. And you can't take your inside bounds and make them your outside bound. This move here that works for rectangles, right? The inside goes to the outside goes to the differentials and bounds. You just do like this. That's a peculiarity of rectangles. It gets weirder when it's not a rectangle. Yeah.
Is that the same for if it's like negative?
I'm sorry?
Does it also just get more complicated when it's like negative?
Oh, you mean like when f is negative?
Yeah.
No, actually that doesn't change anything. It's great, good question. So the only reason that I specifically here said non-negative is because I do want to be able to talk specifically about volume. And volume, I don't want to deal with absolute values and stuff like that. Think back now to single variable calculus. When you're computing the area under a curve, you have to say non-negative because otherwise, when the curve dips below, then you're computing the negative of the area instead of the area. This is it's not a fault of integrals. It's a fault of the question of wanting to compute this awkward thing that's intrinsically positive. How weird is that? Most of the time we want to compute things that are not intrinsically positive, and integrals are perfectly suited for it. So this is not to be worried about right here. It's a peculiarity of the circumstance that we're rarely going to have to deal with. Yeah. It's a great question. Anybody else? All right. Okay, so now here's the next thing we might want to do. There's a bunch of other things that we computed with single variable calculus. So, for example, mass of a rod, where density is given. Right? You got density as a function of x, find the mass of the one-dimensional rod along the x-axis. And we computed area with a single variable integral. We compute the mass of a rod with a single variable integral. Okay, well now we know how to compute a volume under a surface with a iterated integral. Wouldn't you think that a two-dimensional analog of the mass problem? What if I had mass distributed across an area where I know the density as not mass per unit length but mass per unit area? Wouldn't you think I could just kind of do the same thing? Wouldn't you think something like this ought to work? I'm going to put a question mark there just because we're guessing at this point. And I feel like it seems like it ought to work. And it doesn't. And this is unfortunate. But things are just a little bit harder in a multivariable setting. Let me explain first what makes this work and therefore what goes wrong down here that makes this not work. So, specifically, let's look at this part right here. Right, our iterated integral. Why did we multiply f of x, comma y times dx? Well, it's because we were trying to compute a cross-sectional area. We took that area, we chopped it up into little slices of area, and this represents a single little slice of area of our cross-section. And height times length gives me area. And area I understand. Specifically, I know that area accumulates. This is a concept that we're going to use a lot in this class. What I mean by accumulates is that if you have one little strip of area, right, and then right next to it you have another strip of area, this area plus that area tells you the area of what you get when you put them together. So the areas combine in this natural, you just add them. Couldn't be simpler kind of way. Not everything behaves like that. So just as a counterexample, think about concentration. Right? If you have a glass of water that has, it's 5% salt, you have another glass of water that's 10% salt. If you mix them together in a larger glass, does it become 15% salt? No. It doesn't add. Concentrations don't add. They like average or something. Right? So concentrations do not accumulate. Area does. Concentration does not. So we can't take for granted that whatever we might happen to be interested in accumulates. It is because we understand the area that we can conclude with confidence that it accumulates. Okay, now let's try to see if we can go through the same thing here. This is kind of what I would expect. I mean, again, naively, just kind of, I don't know, does this work for volumes? Maybe this ought to work for masses. It kind of seems like it ought to work. But let's think it through. What is this? Keeping in mind, density is mass per unit area. Right? In this scenario, we've got a rectangular sheet. The mass is distributed across area. What do you get when you multiply mass per unit area times length? And it's just a mismatch, right? Mass per unit area was intended to be multiplied by areas. And mass per unit area times area gives you mass. And that's nice. When we know what mass is, we understand mass. Mass accumulates. And that's just not what we have here. It's sad, but it's just not what we have. I mean, look what we've got. We've got here, we've got mass per unit area times length. And it's not a thing that we currently understand. Now you can make units arguments. You can say, oh, okay, well, yeah, but area is length times width, and so maybe this is mass per unit width, right? Maybe. What is that? And does it accumulate? Are we sure, one way or the other, whether that accumulates? There are answers to these questions. It's not that we can't answer these questions. It's that we don't want to have to deal with this every time we come up with here's a new application I'd like to study. Oh gosh, I'm going to have to figure out what's the thing, and does the thing behave the way it's supposed to, and does what I've written down here actually make sense? We don't want to have to go through that every time. So this thing is a problem. And so I'm just going to say, broad stroke, this is not a good approach, because it's going to lead us to a problem every time. Everybody see the problem? That's the bad news. There's good news too, by the way. I mean, there is an answer to this question. It's just that we're going to have to develop this other answer. Okay. And that other answer is called a double integral. Not to be confused with iterated integrals. Not the same thing. This is a brand new idea. Double integrals are an analog, a really better than what we've seen already, a better analog of single variable integrals. And for me to flesh that out, I do need to make sure everybody knows what a single variable integral is. I know y'all know some things about single variable integrals. A lot of students, though, either forget or maybe your high school calculus courses may have swept under the rug that integrals are Riemann sums. So now, in a lot of high school classes, let me speak for my high school class. My high school class, they showed me that an integral was a Riemann sum, and then they said, good news, we don't need to worry about that anymore, because there's a much better way to compute integrals, and it's called the fundamental theorem of calculus, and so, fooey on Riemann sums, let's just use the fundamental theorem. We'll evaluate all of our integrals with the fundamental theorem. And I'm all for that. The thing is, that's not what Riemann sums are for. Riemann sums are not for computing integrals. They're for defining integrals. And very importantly, they are for connecting applications to integrals. So, for example, if you have a question that you want to compute the mass of a rod, right, like we talked about. How do you compute the mass of a rod with an integral? Well, you take your rod, you chop it up into little pieces. On each little piece, you compute mass as density times length, and then you write down your Riemann sum, aka integral, which you then evaluate with the fundamental theorem of calculus and get an answer. And notice, area did not come up in that calculation at all. Now, a lot of high schools, again, don't like Riemann sums, find Riemann sums to be hard or something. And so a lot of high schools will give, I'm going to say, kind of sketchy arguments where they'll say, you know what, mass, it's kind of like an area under a curve. At which point I have to raise my hand and say, I'm sorry, what now? Where'd that come from? In what sense is mass of a one-dimensional thing? There's just a number line. That's it. How is it that mass is area? It's a sketchy argument. And the best versions of these sketchy arguments go like this. They say, well, yeah, but I can take mass and I can kind of chop it up in the way that's very similar to how I would chop up area. And effectively what they're saying is mass is equal to area because they're both computed by the same Riemann sum. So they're not really truly bypassing the Riemann sum. They're just making a bad version of a Riemann sum argument. So it's not a good idea to think of mass as computed by, well, think of it as an area and then compute the area with an integral like that. This whole part of that conversation is like, why? What did the area contribute to this? It contributed nothing. You don't need to think of integrals as area at all. Does that make sense? So why do they do it? Well, it's a very easy reason. Well, the reason a lot of people equate integrals with areas is because it's geometrically satisfying. It's a picture you can look at and feel like you see what it is. And that's nice. And as a visual aid, that's fine. Right? But very importantly, you cannot think of this as the definition of an integral. It's just not right. The integral has to be thought of as a Riemann sum. Okay, if you want to hear more of this rant about the definition of an integral, I'm going to refer you to my YouTube channel. I have a playlist called Miscellaneous Topics, and one of the recordings is called What is an Integral? And there's 30 minutes of me complaining about various different aspects of misunderstandings and that sort of thing about integrals. And there's actually sort of three separate topics that I talk about here. I talk about why I don't like the term indefinite integral. I talk about the misunderstandings about what is an integral in terms of its definition. And I talk about this silly idea of infinitesimals that some people float, which is basically nonsense. And so anyway, I refer you to that. Okay, so let me let's see. We got a minute and a half. Here's going to be our approach for defining a two-dimensional analog of an integral. In single variable, we took our one-dimensional domain and chop it up into little pieces. We can do the same thing two-dimensionally. We just have to chop in two different directions. Because it's a two-dimensional domain, you got to chop it two ways to get little pieces. Okay. On each little piece, like you take a little piece of the x-axis over here, there's various different things that you might want to write down. Oh gosh, I don't know why that does that. I don't know. Oh gosh, where is that? There we go. Okay, so on this little piece, why would I want to multiply some function times delta x? Well, maybe I'm computing the area sitting over this and its height times width. Maybe I'm computing the amount of mass in a one-dimensional rod in this little piece. Well, then it would be mass per unit length times length. Maybe I'm computing the amount of work that it takes to accomplish a certain task. Well, then that amount of work would be force times distance, right? Various different applications, and in all the different applications on each piece, you're multiplying some appropriate integrand times length to get an accumulating quantity, right? So area, mass, work, these are all accumulating quantities, you add them up. We're going to do exactly the analogous thing here, having chopped into little pieces like this. Claim that there's a bunch of circumstances where we're going to want to multiply some function times the area of this little piece. Now, what would those circumstances be? Well, maybe I'm computing the amount of volume sitting over this little piece, in which case it would be height times area. Maybe I want to compute the amount of mass in this little piece. Well, mass would be mass per unit area times area. No mismatch. Mass per unit area times area. It's exactly what mass per unit area was made for, right? Makes perfect sense. Maybe this is the state of Wyoming, and I want to compute the number of the population of Wyoming, and I want to ask how many people live in this little, city block or county or whatever. Well, people per unit area times area gives you the number of people, right? So, same idea. We're multiplying something times size to get an accumulating quantity we can add up. And this is what that looks like when you have a two-dimensional domain. And so this is our definition. In fact, let me do it like this. This then is our definition of what we call a double integral. It's the same basic idea as a single variable integral. It's just adding up over two dimensions instead of adding up over one dimensions. And here's the notation. And real quick last thing, I'll let y'all go. The book spends a bunch of time talking about irregular partitions and test points. And this is all very, very important in a math major real analysis class, which this is not. Right? And so for what we're going to do, we're going to consider, you'll notice here, only continuous functions. And if you have a continuous function, then these don't make any difference at all. And there's no real point in talking about them. So all the book's discussions about irregular partitions and test points, you're welcome to ignore it. You're also welcome to read it if you're curious. But you're welcome to ignore it. We're not going to use that in this course. Y'all have a good day. See you later.